Welcome to Brain Vision.
In this problem, we're going to be looking at power radiated by the sun out in all directions into space. That power is equal to 3.9 times 10 to the 26 watts. And the Earth, at some distance away from the sun, that distance is 1.5 times 10 to the 11 meters. Well, some of this power from the sun is going to reach the Earth, and we know that it'll have an intensity, we'll call that S, an intensity when it reaches the surface of the Earth there. Now, what we're trying to find is how much power is going to strike a small patch of land on the Earth's equator. And to do so, we need to know what's the intensity of light that's reaching the Earth there. So that would be step one. We know the total power that the sun radiates in all directions. So let's imagine for a second that that power is being radiated into this big sphere that surrounds the sun out into space. That power then is equal to intensity times area, and so the area is the area of this big sphere where all the sun's power is being radiated to. Area of a sphere is 4 pi times the radius squared. The radius in this case is that distance from the sun to the Earth. So 4 pi times 1.5 times 10 to the 11, square that whole thing. And if you plug that into your calculator, we get something like 2.8274 times 10 to the 23 meters squared. And so that's this area where all the sun's power is being distributed. If we go back to our equation here, what we're trying to solve for is the intensity. So I'll rewrite the equation for intensity as power divided by area. And we can plug in those values that we have now. 3.9 times 10 to the 26 watts, the power, divided by the area. 2.8274 times 10 to the 23rd meters squared. About 1,379 watts. So that's the intensity of light that's reaching the surface of the Earth. Let's zoom in a little bit and take a look at the Earth here. So here's the light from the sun coming in towards the Earth. Comes in this way, and we can draw in a line. This is perpendicular to that. The Earth is actually tilted on an axis. So if this is the north-south axis of the Earth, that tilts away from the sun about 27 degrees like that. And so the equator, which is perpendicular to that north-south axis, we can take a look at a point Q along the equator and think about the light that hits the Earth at that point. Let me zoom in even closer for us to take a good look at that. So here's the surface of the Earth. Here's the equator. And our point Q. Now the light that comes in and strikes that point, we're going to see that it connects with the equator at an angle that is also 27 degrees based on the trigonometry of it. You've got the equator and the north-south axis of the Earth that's perpendicular to each other, and that's 27 degrees clockwise from this perpendicular axis to the sun. Therefore, the equator has to be 27 degrees clockwise from the sun's incident radiation. So knowing that this is 27 degrees right here, we'll be able to figure out that the intensity of light, so in this direction, the intensity of the light that's perpendicular to the surface, that's going to be S times cosine of 27 degrees. That's going to tell us how much power is actually spread out across this area by looking at the component of it perpendicular to that surface area. So now let's take our value for the intensity, 1379, and multiply by cosine of 27 degrees. That gives us about 1.229 times 10 to the third, or 1,229 watts. So out of that 1,379 watts, it's actually only getting 1,229 watts because of the fact that it's tilted away from the sun. So less of the intensity is reaching that area. Now that we know what that intensity is, we can go ahead and go back to our equation up here, P equals SA. We're going to look for P, the power, at that point. So P at that point Q then is equal to S at that point, the intensity, 1,229, times the area. They've told us that the power is striking an area of land that's 0.75 square meters. And when we multiply that together, you'll get about 920 watts.